and I will share my screen. Okay, can you see my screen? Can you hear my voice?
Boleh, doktor.
Okay, thank you for the response. Okay, so last week we have learned about this double conversion FM receiver block diagram. And for your information, this is uh, the real system that has been used nowadays. Even nowadays, we are still using a double conversion FM receiver. Okay, so if you remember in the amplitude modulation, when we learn about the AM receiver has one mixer converter. That means in AM, we are doing only once frequency down conversion from RF frequencies band into intermediate frequency. Okay, but for the FM, we cannot do like that because the frequency of FM band is higher, which is between the 88 megahertz until 108 megahertz. So the frequency is in terms of mega, so which is very high. So what we need to do is we need to do down conversion 2 times. That means the receiver needs to have 2 mixer converter to do the down conversion twice. Okay, so as I've mentioned earlier last week, okay, let's go through again. Let's go through again what we have learned last week. Okay, so if you see from this picture, the antenna, for example, antenna receive all the frequencies band. Okay, so the antenna receive frequencies, FM frequencies between 88 megahertz until 108 megahertz. Okay, so this frequency range is very big. Okay, 20 megahertz of bandwidth is very big, so we cannot process all of this all together. Okay, so for example, now I want to listen to one radio station only. Last week I gave example about Era FM. If you remember, Era FM is the frequency is 104.5 megahertz. Okay, for example. Okay, so that means the preselector, okay, the preselector needs to tune to this frequency. Okay, so the preselector needs to tune to this frequency, which is 104.5. so when I tune my radio, I'm actually tuning the preselector so that the center frequency would be at 104.5. Okay, so the preselector will limit the accepted bandwidth. Okay, it will select a small portion of bandwidth, and it will let it go through the next process. Okay, so the next process would be the RF amplifier, which will amplify the amplitude of the received signal, because the received signal has a low amplitudes due to the attenuation. Okay, so the signal has traveled long distance from transmitter to the receiver, so of course there's a lot of attenuations process happens in the middle. So what we need to do is we need to amplify the amplitude of the signal, so that easy for us to do the next process. Okay, and then what? The next process is the first down conversion. So we send the signal through the first mixer converter. Okay, so mixer converter, if you remember that mixer is the symbol is X, like this. So if you draw the picture, is it is something like this. So I draw up here. So mixer converter will receive at least two input. Okay, one input is from the local oscillator, and another input is from the input signal. Okay, so the local oscillator, as we learned in the previous slides, the process would be either it is a high side injection or low side injection. Okay, so if you remember that for high side injection, we want to find the FIF. FIF is equal to FLO minus FRF. Okay, this is if we use a high side injection where the frequency of the local oscillator is higher than the input signal frequency. Okay, because we don't want to we don't want to produce a negative frequency. Okay, and if we use a low side injection, that means the local oscillator frequency is lower than the FRF. So we can find the intermediate frequency, which is FRF minus FLO. Okay, so FRF is the received signal, FLO is the local oscillator frequency. Okay, so this is for the low side injection. And as we have learned previously that in practical cases, normally we use a high side injection. Okay, normally in the practical case we use a high side injection. Okay, and what we want to do here in the first mixer is that we want to produce the first IF. Okay, we want to produce the first intermediate frequency. Okay, so in FM there are two intermediate frequency, okay, which is what we call as a first IF. Okay, the first IF. Okay, the first IF is equal to 10.7 megahertz. Okay, and the second IF that we want to produce is, okay, second IF is 455 kilohertz. So second IF is similar with the intermediate frequency in the amplitude modulation. Okay, so this 10.7 and also the 455 kilohertz, this is the center frequency of intermediate frequency. Okay, so how does the mixer converter do the process to find the intermediate frequency? Okay, so remember in the down conversion, we are actually multiplying two inputs mathematically. Okay, when we multiply two inputs in the mixer converter, we are actually producing a upper sideband and also the lower sideband. Okay, so in the first mixer, okay, in the mixer, so when two inputs are mixed together, that means we're going to produce, okay, that means we're going to produce upper sideband and also the lower sideband. And in this case, the lower sideband would be the intermediate frequency. Okay, so FLSB produced through the mixer converter is equal to F local oscillator minus the input signal F RF. Okay, so this is actually the F IF, the first IF. Okay, why is it like this? Okay, because when we want to do the down conversion, we are planning to down convert high frequency into lower frequency. Okay, apabila kita melakukan proses down conversion, sebenarnya yang kita inginkan adalah frekuensi yang rendah, bukan frekuensi yang tinggi. So the upper frequency produced by the mixer converter USB, this is actually FLO plus FRF. Okay, so the signal that we want to produce is actually this one. Okay, and we already know how much is sorry, wait. Okay. Baik. Okay. So we already know how much is the value of IF. Okay, we already know the IF frequency that we want actually by standard. Okay, by standard it is 10.7 and also the 455 kilohertz. Okay, so last week I gave you two examples. If we use a high side injection or if we use a low side injection. Okay, so for example, we want to find the local oscillator frequency. Okay, if we use a high side injection or low side injection. So how to do this? Okay, so in order to find the FLO, okay, that means FIF 1 plus FRF, we can find this one for the high side injection. Okay, so I use a high side injection equation. I use a high side injection equation to find the local oscillator frequency. So we have two possibilities of FLO. Okay, kita ada dua kemungkinan FLO. So this is 10.7. So we can do this 10.7 megahertz plus the input here is the radio frequency that I want to listen, which is 104.5 megahertz. So I need local oscillator frequency of 115.2. This is point. So you can try use your calculator. Okay, try use your calculator. 115.2 megahertz. Okay, so this is if I use a high side injection. Okay, high side injection. What if I use a low side injection? How much is the local oscillator frequency that I need? Okay, kalau saya gunakan high side injection, berapa banyak how much is the local oscillator frequency? So let's try to find it. Okay, so actually here I try to explain to you two version, high side injection and also the low side injection. So that means if I use a low side injection, that means the local oscillator frequency is lower than the input RF signal. Okay, that means FRF minus FIF 1. Okay, so this is equal to 104.5. This is the radio frequency that I want to listen, minus the first IF is 10.7 megahertz. Okay, so I need a frequency of local oscillator for about 93.8 megahertz. Okay, so this is a low side injection. Okay, so now, okay, now I I need to know what is the frequency produced by the first mixer. Okay, so the frequency produced by the first mixer is the FLSB, okay, and also FUSB. Okay, so what is FUSB and FLSB? FLSB is the lower frequency, which is the intermediate frequency, okay, and FUSB is the higher frequency that we don't want actually. We can remove it through the filter, okay. So how much is the FUSB that produced by the first mixer? How much? Okay, I know that the FLSB that I want to produce is the first mixer, so is the first IF, okay, which is 10.7 megahertz. Okay, so the FUSB, the upper sideband, for example, if I use a high side injection, okay, katalah saya gunakan high side injection, okay, that means I produce the upper side frequency for about so I use a high side injection, this one, so this is actually FLO plus FRF. Okay, so the local oscillator that I want to show you here is actually from the high side injection. Okay, for example, I want to use a high side injection, for example, okay, so 115.2 megahertz plus FRF here is 104.5 megahertz. Okay, so this is the frequency for about 219.7 megahertz. So I don't want this frequency actually, okay, but this is the upper side frequency produced through the mixer converter. Okay, what about if I use a low side injection? If I use a low side injection, that means I gonna produce the upper side frequency is, sorry, yeah, so this is actually continuous circuit. So FUSB here is equal to FLO from the low side injection plus FRF. Okay, this is if I use a low side injection. So low side injection, we already find this, the value is 93.8, okay, from the previous calculation, which is 93.8 megahertz, plus the radio station that I want to listen, which is 104.5 megahertz. Okay, so this is for about, the value is 198.3 megahertz. Okay, this is if we use a low side injection. Okay, however, normally most of the time we use high side injection, okay, which is FUSB, we will produce 219.7, and the lower sideband that produced through the first mixer is 10.7 megahertz. Okay, so here in the first the output of the first mixer is 10.7 megahertz, and also the upper sideband. So the upper sideband depend on the local oscillator frequency. Okay, let's say I use high side injection, that means it will produce 219.7 and also 10.7 megahertz. Okay, so katalah I use a high side injection, so that means here is 219 to sorry, 219. So I just put it here. So 219.7 megahertz, and also 10.7 megahertz. Okay, so this is the first mixer. Okay, so and then we have a bandpass filter over here. So the bandpass filter will only select the lower frequency and remove the higher frequency. So it will let through the 10.7 megahertz of frequency. Okay, 10.7 megahertz of frequency to the second mixer. Okay, so the second mixer will do the same process again. Okay, it will produce FLSB and also FUSB, and then also FUSB. Okay, FUSB and FLSB. So how much is local oscillator? It depends. We can use high side injection, we can use a low side injection. And we already know that the second IF would be 455. Okay, so now again we use as we calculate previously, that FLSB, okay, FLSB is equal to FLO minus FR minus FIF1 . Okay, so now the input is not FRF anymore, it is FIF1. Okay, FIF. We are not using FRF because the input now is FIF, first FIF. Okay, the input to the second mixer is the first intermediate frequency. Okay, so we're going to produce this for about this is for IF2. Okay, for IF2, and the upper sideband is equal to, okay, FLO. So this is FLO2, so I put FLO2. So FLO2 plus FIF1. Okay, so now the issue is, how much is the upper sideband produced by the second mixer? How much? Okay, we can do the calculation. Okay, we can do the calculation. For example, if we use a high side injection, so let's do the calculation here to find the FLO. Okay, to find the FLO. For example, we want to use a high side injection. Remember, FLO2 is equal to FIF1 plus the input plus FIF2. Okay, so FIF. Okay, why is it like this? Why is it like this? Okay, so if you compare with the above equations, FIF1 plus FRF, now we want to produce FIF2. That means the input here is FIF1 plus FIF2. So the high side injection is a frequency higher than the first IF. Okay, if this is a high side injection, that means the local oscillator frequency FLO2 must be higher than the first IF. Okay, kalau ini adalah high side injection, bermakna FLO2 mestilah lebih besar daripada input FIF1. Okay, so that means this is 10.7 megahertz plus FIF2 is 455 kilohertz. Okay, so this is we're going to produce 11.155 megahertz. Okay, so this is a high side injection. This is the local oscillator frequency that we need if we use a high side injection. Okay, and if we use a low side injection, okay, let's say I do here. So maybe I erase a little bit, for example. Okay, so let's try to do it here. So if I use a low side injection, what happened is that FLO2 would be equal to FIF1 minus FIF2. Why? Because if this is a low side injection, that means the local oscillator frequency must be less than the input, which is the first intermediate frequency. So this is equal to 10.7 megahertz minus 455 kilohertz. Okay, and this is equal to 10.245 10.245 megahertz. So this is a low side injection. So if I use a low side injection method, that means my local oscillator must be less than the input. Okay, so now we have two possibilities of LO. So it's up to us to choose when we do the system. Okay, kita terpulang kepada kita nak gunakan yang mana satu. So that means we need to use either one of these frequency for the local oscillator. Okay, so now we want to know how much is the upper side band produced by the second mixer. Okay, let's say we use a high side injection. So FUSB using high side injection equal to FLO2 plus FIF2. Okay, FLO2 plus FIF1 Okay, using this equation FIF1, so that means this is equal to 11.55. So I want to use a high side injection. Okay, so this is 11.155 mega plus 455k. Okay, so this is 21.855. So 21.855 megahertz. So if I use high side injection, I will produce FUSB 21.855. So this is if I use high side injection. What about if I use a low side injection? So if I use a low side injection, that means I use a low frequency of local oscillator. So the upper side band that I will produce if I use low side injection, for example, okay, That means this is FLO to plus FIF1. Okay, we still use the same frequency but different value of local oscillator. So this is 10 point this one 245 plus 45. Sorry, this is mega. If you don't understand, please ask me before I move further away. Okay, 10.245 mega. Sorry. So 10.245 mega. So 10.245 mega plus 455 K. So this is equal to how much is this? This is equal to 20.945 megahertz. Okay, so we have two options. Actually, we have two options. We want to use a high side injection or low side injection. Okay, let's say I'm using a high side injection, for example. Okay, let's say I choose high side injection. That means the lower frequency produced by the second mixer is the 455 kilohertz, which is the second IF. Okay, and the upper side band, if I use the high side injection now, so that means the upper side band is 21.855. So this is 21.855 mega. Okay, remember the second mixer, the purpose of the second mixer is to further reduce the frequency to become second IF. So therefore I don't need the upper side band. The upper side band, the higher frequency, needs to be removed, which is done by the band pass filter. The band pass filter will select the lower frequency, which is the second IF. Okay, so the second IF, 455 kilohertz, center at 455 kilohertz, will be passed through the filter. Okay, and then it goes to the IF amplifier to amplify the amplitude. Okay, and then band pass filter, okay, to filter out all the other harmonics. Okay, so that I will only receive a single channel, okay, which is center at 455 kilohertz of intermediate frequency. Okay, so this band pass filter will remove the unwanted harmonics. Okay, and then it goes through the limiter. Limiter will adjust the amplitudes of the signal. Okay, and then it will do the demodulation process. Demodulation process is to produce the VMT. Okay, and then de-emphasis, we will reduce the amplitude of the signal with the same factor as we have done in the transmitter to increase the amplitude. Okay, so and then it will pass through the audio amplifiers to increase the amplitudes which is suitable for the speaker. Okay, so I will listen to the era FM. Okay, I hope that you understand. Okay, I hope that you understand. So the mixer, the process in the mixer is just to plus and minus. Okay, processed in the mixer just to produce two types of frequency, lower frequency and upper frequency. Lower frequency is the intermediate frequency that we want, and the upper frequency is the frequency that we don't want. Okay, and I already show you what happened if we use a high side injection, low side injection. High side injection, low side injection is just to determine the value of the local oscillator frequency. Okay, so high side injection, low side injection cuma untuk menentukan frekuensi local oscillator. Okay, mixer converter produce at least two frequencies to the output. Okay, which is the IF or the up and also the upper sideband. We want the intermediate frequency. We want the low frequency. Okay, so the frequency is go down, down, down until we get the VMT. Okay, the bandpass filter helps to filter out the higher frequency or the harmonics. Okay, and remember the second IF would be 455 kilohertz. From there, 455 kilohertz, we can do the demodulation process to produce the VMT. So you see from here, in FM, we do twice down conversion before we do the demodulation process. Different from the AM, where we only do once down conversions, then we do the demodulation process. Okay, so I hope that you can familiar with this kind of calculation. Why? Because this kind of calculation has been asked in the quiz. Okay, this kind of calculation has been asked in the quiz, especially the calculation in the mixer to produce upper and lower frequency. Okay, pernah ditanya dalam quiz, objective question in the author, what is the frequency at the first mixer and also the second mixer, given the input frequency is how much? We give you the input frequency and we give you the local oscillator frequency, and how much is the output of the first mixer and also the second mixer. It is very easy question. Okay, it's just a plus and minus only. For lower sideband, you minus with the local oscillator frequency. For upper sideband, you plus with the local oscillator frequency. Simple as that. Okay. Anybody want to ask question about this? Ada soalan tak nak tanya? Anybody? Tak ada, eh? And this might be come out in the quiz later, maybe. Okay. So previously we asked how much is the frequency from the first and second mixer. Okay, you just need to plus and minus. Plus to get the upper frequency, minus to get the lower frequency. That's it. Okay. Before we proceed, can I get your response? Are you still there, students? Anybody can respond?
Yes, it is.
Okay, thank you for the response. So if you don't have question, I will move to the next slide. Boleh, eh? Kalau tak ada soalan, saya teruskan, eh? Okay. So the slope detector. Okay. So what is this? So previously we looked from the broad perspective of receiver. Okay. Now we want to see the process inside the demodulator, this part. Okay. So there are many types of demodulator. The first one is the slope detector. Okay. So the slope detector, like this. This is a simple circuit of slope detector. The most simple demodulator circuit is this one, a slope detector. Okay. And here the slope detector is designed so that the center, the tuning frequency, okay, the what they call the oscillation frequency. Center of the oscillation frequency is within the center of the most steep curve here of the frequency response curve. Okay, so what is this curve actually? This is the frequency response curve of the circuit. Okay, so it is designed so that the tuning frequency must be at the center of the most steep curve here. Okay, and if the frequency of the input change from rest to the maximum, okay, it will produce the positive cycle, this one. And if the frequency of the input change from rest to the minimum, okay, which is this one, what happen is that it will produce the negative cycle to the output. Okay, so that means the frequency variation of the input will produce voltage variation at the output. Okay, so the demodulator will keep on track the frequency changes from the input, and it will produce the amplitude variation to the output. Okay, so as stated here, the circuit is designed so that the intermediate frequency, center frequency, falls in the center of the most linear portion of the voltage versus frequency curve. Okay, so the FC here, this is the center. So this is the FC of the center of the IF. Okay, the center of the IF center. Okay, it's not the carrier frequency in the RF band. It is actually the carrier frequency after we have converted it to the intermediate frequency. Okay, so when IF deviates above FC, the output voltage increase, and when IF deviates below FC, the output voltage will decrease. So therefore, the tuned circuit converts frequency variation to the amplitude variation at the output. Okay, and this circuit has a disadvantage. Gain is reduced, difficult to achieve, linear slope response curve. So there are many disadvantages for this kind of demodulator circuit or detector circuit. Okay, and then what? We have the second type of demodulator, what we call as a balanced slope detector. So balanced slope detector consists of two slope detector. Dia terdiri daripada dua slope detector, above and below. So part A, the first slope detector is the above, second is the below, A and B. Okay, and for this balanced slope detector, when the input is at rest frequency or at the center of IF, the output will produce 0 voltage. Okay, and then when the input frequency change from the center of IF until the maximum, it will produce the output voltage towards maximum at positive cycle. And when the input frequency becomes minimum, okay, from the center of IF until minus delta F, then the output will be towards negative peak voltage. So that means if the frequency becomes higher, it will produce positive output voltage. If the frequency becomes lower, it will produce negative output voltage. Okay, okay, so at resonant frequency it will be 0. Okay, resonant is the center of IF. Okay, as the IF deviates above the center frequency, the top tuned circuit will produce higher voltage than the lower tank voltage. So that's why you're going to produce a positive output. And when the IF frequencies at the input deviates below the center frequency, the top tuned circuit produce lower voltage than the lower tank circuit, and it will produce negative output voltage. Okay, so what is the tank circuit? The first tank circuit here, and also the second tank circuit above and below. Okay, so there are advantage and also disadvantage of this detector circuit or demodulator circuit. Okay, and we move to the third demodulator circuit, which is what we call as the phase lock loop, PLL. Okay, so PLL is the most popular demodulator circuit available in the real world. Okay, we are still using PLL nowadays. Okay, there are many kind of PLL. Okay, so PLL is the most popular demodulator circuit for the FM radio. Okay, so PLL is this one. So PLL demodulator is this is the block diagram of the PLL. If you see from this picture, okay. So how does the PLL works? Okay, I will show you. Okay, so maybe before I show you, I will show you this. Before I explain about this, maybe I should explain about this. So PLL has 3 operating states. This is a free running, capture, and then lock state. Okay, free running state means that there's no internal input frequency. The feedback loop is open, so that means that there's no input frequency in the input. Okay, so okay, sorry, I think maybe I should explain about this first. Sorry. Okay, let me explain about this first, so that later we're gonna go through these phases. Okay, okay, okay. Let me explain about this. Okay, so this is the block diagram of the PLL. Again, PLL has many types, depending on the application. Okay, so the PLL here, if you see, it has a phase detector, low pass filter, amplifier, and here it has a voltage control oscillator, VCO. So how does it works? So the first thing is that it will compare the input. Okay, it will compare the frequency at the input. Okay, so you see that here is a FM input. The input here is a FM signal. That means the input change in terms of frequency. Okay, and for example, here is a FI, F input. So here is a FO is the output of the VCO, FO. Okay, so phase detector will produce error voltage, what we call as a VD. Okay, it will compare. Okay, it will compare the input. Okay, because VD is equal to delta F multiplied with KD. What is delta F? So delta F is equal to the difference of the input, F input, Fi, minus F from the voltage control oscillator. Okay, so the phase detector will keep on measure the difference of frequency. It will produce the delta F. So delta F multiplied with the phase detector sensitivity parameter KD, so it will produce VD at the output. Okay, so the output here is actually in terms of voltage. Okay, it will produce output voltage. So the frequency difference produce output voltage, VD. Okay, and then this VD will go through the low pass filter. Actually, the low pass filter has a transfer function of KF. okay, K filter, okay, which is the sensitivity parameter for the filter. We call it as KF. Okay, so KF, here is VF, VF. Sorry, I don't know why it's always like this, VF. So VF. Okay, so VF. So VF is equal to equal to KF VD, KF multiplied with VD. Okay, so it is actually equal to KF KD delta F, because VD is KD multiplied with the frequency difference. Okay, and then V out. So V out here is equal to this V out here is equal to KF. So V out is equal to KF KD KA delta F. So it will produce the output voltage, and this output voltage also will be looped into the voltage control oscillator. Okay, so this voltage control oscillator will compare, okay, it will compare the input and produce the output. Okay, so the FO here produced by the voltage control oscillator, it measures the difference in terms of voltage. Okay, and what happened is that the output produced by the here is FO is equal to Fn. Fn here is the voltage control oscillator at natural frequency, rest frequency. Okay, plus delta F. So how much is delta F? So delta F, this one has also the transfer function of KO, for example KO. So delta F, the difference in terms of frequency is actually equal to from the V out. Okay, from the V out we get V out multiplied with KO, K0, KO from the, this is the sensitivity parameter for the voltage control oscillator. Okay, so this is gonna be delta F. V out here is this one, KF KD KA multiplied with delta F from the input. So this is actually delta F from the input. Okay, so it produced delta F over here. So from this delta F we can produce the FO. FO is Fn, the natural frequency of the voltage control oscillator, plus the delta F, the difference of frequency. So we produce delta F based on the sensitivity parameter of the VCO. Okay, so it will produce the FO, and it will be inserted to the phase detector again. Okay, so that means in the VCO, voltage control oscillator, what it will do is that it compare the input voltage, the difference in terms of input voltage, produce the output frequency. Okay, VCO ini dia akan compare voltage dan menghasilkan output frequency. Okay, so if you see from here, from this process, the phase detector will always check the input. Is there any input or not? if there's an input, it will start comparing. How much is the difference in term of input frequency? Okay, kalau ada input, barulah dia akan start mengukur perbezaan dari segi frekuensi itu. What happen if there's no input? Okay, what happen if there's no input here? That means it will always looping in the same frequency. No change. Okay, so the VCO, the system will be at rest when there is no input. But when there is an input, it will start comparing to find the desired frequency. Okay, so for example, I want to listen to Era FM like previously. Okay, I want to listen to Era FM, and it will compare the input to find the intermediate frequency of 455 kilohertz. Then it will do the output process, because this is a demodulator. Okay, so once it receives the signal, it will start comparing to find the desired frequency band for the demodulation. Okay, so that's why we have these three states. Okay, so for your information, this is the most popular question in the final exam. We have asked this many times in the previous semesters about this. Okay, explain about the three phases of PLL. Okay, free running, capture, and lock state. Okay, so free running, there's no external input. As I mentioned earlier, there's no input FM. Tidak ada input. Okay, the feedback loop is open. So the voltage control oscillator will oscillate at its natural frequency, which is Fn. Okay, like we have learned previously, Fn, the natural frequency. There's no input. So the system will run at its natural state. Nothing happened. Okay, nothing happened. Then what? Then there's input. Adanya input. Okay, so when there's input, that means the phase detector will start comparing to find the desired frequency. Okay, so there must be external input and the feedback loop must be complete. So there will be feedback. PLL in the phase of acquiring the phase lock. PLL here, the system is try to find the desired frequency. Okay, not just a random frequency, it will find the desired frequency. Okay, so capture state is the process of finding the desired frequency. Okay, and then what? Lock state. Lock state means that the system already found the desired frequency. Okay, what happened? That means the phase detector already find the resonant frequency that we want. Okay, once it find the desired frequency, it will lock to that frequency changes. For example, the phase detector lock at 455 kilohertz, which is the second IF, for example. From there, it will keep on track the changes of the input. Okay, so once the system find the desired frequency, it will lock to that frequency and keep on comparing the difference. Okay, so the lock means that we found the desired frequency, and we will keep track the changes. Once kita dah dapat frekuensi yang diinginkan, dia akan lock pada frekuensi itu dan sentiasa mengukur dia punya perubahan. Okay, so lock state, we already found the desired frequency. We want to track the changes. Okay, so the VCO output frequency is locked into or equal to the frequency of the external input. So the VCO output frequency track follows the changes of the frequency of the external input signal. Okay, so the frequency difference in the input produce a voltage difference at the output. Okay. So this is you can read this. I already explained all of this, and here you see that VR is delta F KD KA. So I add a KF here for the low pass filter. Okay, actually you can add KF here for the low pass filter. Okay, so we have all the sensitivity parameter for each of the phase detector, low pass filter, and also the amplifier. Okay. Super heterodyne receiver. So we have learned about super heterodyne receiver. Super heterodyne receiver, like the double down conversion receiver that we have learned previously. Okay, so this is the super heterodyne receiver. So super heterodyne receiver is actually the receiver system that we learned previously. This one, the double down conversion, this one. This is a super heterodyne receiver which use double conversion. Okay, double down conversion of the signal. So this is what we call as super heterodyne. Okay, so this is the name is a Armstrong receiver. Okay, which use a double conversion signal. Okay. Okay, so you see that the here similar with previously, actually we need a second mixer converter to down convert the frequency. So we get the first IF is the 10.7 megahertz by standard, and the second intermediate frequency center at 455 kilohertz. That one also by standard. Okay, by standard we have two intermediate frequency, which is 10.7 megahertz for the first intermediate frequency, and then 455 kilohertz for the second intermediate frequency. Okay. Okay, so I've explained all about this, and then FM and PM comparison. So FM and PM comparison. What is the difference between frequency modulation and also the phase modulation? Also, what's the difference? So the maximum frequency deviation delta F depends upon the amplitude of the voltage and also the modulating frequency. Maximum frequency deviation. So delta F is equal to KF KF VM. So the maximum frequency and modulating frequency, KF VM. Yeah, KF VM. So this is actually depending on the KF VM. Why is that? Okay, KF. So okay. So actually the statement is quite confusing. Maximum frequency deviation depends upon the amplitude of the modulating voltage and also modulating frequency. Okay, the maximum phase deviation depends only upon the modulating signal voltage. Okay, so this is actually delta F, and this is, I think, depends on the modulation index actually. Okay, so this is a bit confusing. Frequency of the carrier is modulated by the modulating signal. Phase of the carrier, okay, so this is true. Modulation index is increased as the modulation frequency is reduced. So this is actually depending on this actually. So beta is equal to delta F over modulating frequency. Okay, so if the modulating frequency is higher, that means beta would be smaller. While for this, beta P is equal to KF, so KP VM. Okay, KP VM. It is not depending on the modulating signal frequency. Okay, so this is actually KF VM, kf Vm over Fm. Okay. And if you see in terms of graph, okay, so M here is actually the beta. So this is actually beta parameter. So beta parameter is proportional. If you see, if you remember here, beta f is equal to kf Vm over Fm. Beta p here is equal to kp Vm. So both modulation index is proportional to the modulating signal voltage. The higher the Vm, the higher would be the modulation voltage, modulation index. Okay, and then what? For the next graph, you see that here, beta versus modulating signal frequency. So for Pm, the modulation index is not depending on the frequency. Regardless of the frequency, does not matter. Okay, so as the frequency change, nothing happened to the as the modulating signal frequency change, nothing happened to the modulation index. Okay, and for the Fm, the higher the modulating signal frequency, the lower would be the modulation index, beta f. Okay, so this is actually referring to beta p, and this is beta f. Okay, and then what? Delta theta. So delta theta versus Vm. Okay, so delta theta is equal to kp Vm. Okay, so the higher the Vm, the higher would be the delta theta. Similar with delta f. So delta f is equal to kf Vm. The higher the modulating signal voltage, the higher would be the frequency deviation. Okay. Several advantages of angle modulation over amplitude modulation. So what are the difference between angle modulation over amplitude modulation? So in angle modulation, we're gonna the noise would be reduced far from the AM. Okay, AM signal. Amplitude modulation has higher noise compared to the angle modulation, which is the FM. Improve system fidelity. Okay, fidelity is the continuous attenuations. Okay, when the signal travels from transmitter to the receiver, it come across with a lot of attenuation. So this is what we call as the fidelity. Okay, so in angle modulation, the fidelity would be reduced compared to the AM. Okay, we're gonna produce a better amplitude of the signal at the receiver. Okay, more efficient use of power. Okay, more efficient use of power compared to the amplitude modulation. So it has a few disadvantages depending on the applications. Okay, it has a wider bandwidth. Okay, and more complex circuit. Okay, so frequency modulation FM has a more complex circuit compared to the amplitude modulation circuit. Okay, so these are among the general advantages and also the disadvantages. Okay, so of course we always listen to the FM radio compared to the AM radio. So any of you still listen to AM radio? Ada lagi ke yang masih dengar AM radio? Okay, so normally we listen to the FM radio. Okay, there are many radio stations here. Normally when I drive to work, I listen to one of the radio stations, for example Surya FM, Sinar FM, and so on. So that one is a FM frequency band, FM radio. Okay, AM radio you can try. You can find the BBC radio also in the AM wave. okay, and other radio stations. So AM radio is it's not popular actually, but it is still exists until now, okay. And that's it, okay, for chapter 3. Okay, so we have finished chapter 3 complete, okay. And then what? Of course, when we finish chapter 3, that means we need to continue to chapter 4, okay. So maybe we should take a break. Do you want a 5 minutes break or 10 minutes break? Any response? Or should I proceed?
10 minutes.
Okay, boleh 10 minutes So okay, 10 minutes. I will start again 3:28. Okay, 3:28 10 minutes from now boleh So you can go anywhere you like. I want to make a coffee so that I want to drink coffee. I will continue again 3:28. Okay, so make sure you come again in the class 3:28. Okay, so see you another 10 minutes. Okay, shall we continue again? Are you still there, students?
Yes, doctor.
Okay, thank you for the response. I hope everybody is already in the class. Saya harap semua sudah ada. I hope everybody has returned to the class. We will continue with chapter 4. Okay. So, okay. Before that, can I get your response again? Can you see my screen? Can you hear my voice?
Can, doctor?
Okay, thank you.
Yes, doctor.
Okay, thank you for the response. Okay, so chapter 4 is about the digital system. Again, we will learn something similar with chapter 3, but now we are learning about the process inside the digital system. Okay, so you will learn again about the modulation and also the transmission process, but this time is done by the digital system, digital transmitter and also the digital receiver. Okay. So there are many advantages of digital communication compared to the analog system. Okay, so when we talk about digital, okay, remember my drawing from the first chapter. I draw like this. I draw like this. For example, transmitter. Maybe I draw here. Easy. So transmitter, and here is the channel or medium. Here is the receiver. Again, this is my favorite picture. Okay. So in digital, we have the flexibility to receive analog input, and we also have the flexibility to receive digital input. Okay, and in digital system, we will process the input in term of digital. So that means if the input is analog, we need to convert it into digital. Then we can do the next process. If the input is already in digital, then we can straight away do the next process. Okay, so the process happens inside the system is in terms of digital processing. Okay, and again, we have the option to transmit into the channel. Either we want to transmit as analog, or we want to send it as digital. And normally, if we want to send as a digital, we send it through the wired medium normally. Okay, as a digital pulses. Okay, so we receive analog or we receive as digital into the receiver. The receiver will process it as a digital, and the receiver has the option. Either it want to proceed with digital output, or it want to convert it into analog. So you see the flexibility of the digital system. Okay, this is one of the beauty of the digital system, that we have the flexibility to process the signal. Okay, and when we mention about the advantage, okay, the advantages, the first one here is the noise immunity. So in digital signal, not necessary to evaluate the precise amplitude frequency of the phase. Okay, so in digital system, all input, all signals have only two possibilities, either as logic 1 or logic 0. Okay, all signal, have only two possibilities: logic 1, logic 0, 1, 0, 1, 0. So this is different from the analog. Analog has infinite shape of signals, different in terms of amplitudes, frequency, phase, and so on. But in digital, everything looks the same. Okay, in terms of 1, 0, 1, 0, 1, 0. So it is more easy to detect the error and correct the error. Okay, so it is because noise here is that in terms of disturbance from different kind of frequencies. So in digital, easy for us to eliminate the unwanted signal, easy for us to detect the error. Okay, and in this case, we don't need to necessarily to evaluate the precise amplitude, frequency, or phase of the signal, because everything is in terms of 1, 0, 1, 0. Okay, so there's no there will be no error in determining the correct the precise output signal in terms of amplitudes, frequency, and phase, like we have done previously. Okay, so it is more immune towards noise. And then what? Multiplex. Multiplex, we can combine many signals together easily. So multiplexing is more easier compared to the process happen in the analog. Why? Because every signal looks the same, 1, 0, 1, 0, in terms of logic 1, 0, 1, 0. So easy for us to do the combine. Okay, easy for us to combine the signal because all of them are in the form of logic 1, logic 0. Okay, so much easier. So that means we can combine many input signal easily, and we can transmit it together into the medium. Okay, and then what? Signal regeneration. This is one of the big advantages of the digital system. Regeneration means that we regenerate the signal again. Okay, maksudnya kita hidupkan semula signal itu. So this is different from amplification. Amplification, we amplify the amplitude. Okay, but regenerate means that we regenerate the signal again in between transmitter and receiver. So when we regenerate the signal, we can send the signal towards long distance compared to the analog. Analog signal, okay, analog signal we cannot do the regeneration. Okay, because analog system we cannot do the regeneration because analog signal has a infinite shapes of signals, which is very difficult and complex. Okay, because they are different. Okay, we cannot do the regeneration. Okay, so digital signal can be transmitted further distance, longer distance, because we can regenerate again the signal. Compared to the analog, we can only amplify the signal, we cannot regenerate. Okay, that's the difference. Error corrections means that we can correct the error. Error corrections means like this. So for example, transmitter, for example, I'm sending data 101010. Okay, and suddenly at the receiver side, I'm receiving 111010. Okay, so this is what we call as a bit error. Okay, so in digital system, it has the capability to detect the error and do the corrections. Okay, so for example, like this, it detects the error and it will do the corrections to become 10 10 10. So the chances of errors happens in the system, although it is higher, but we can do the corrections. It has the capability to correct the errors. Okay, so that's the advantage. But it also has disadvantage. Okay, among them is it requires more bandwidth. Okay, digital system requires more bandwidth because we are going to insert many additional bits for the purpose of error correction and error detection. So when we add additional bits towards the transmission, that means we are using wider bandwidth. But the good thing about higher bandwidth is that we can have higher transmission rate, data rate. That means if we use a wider bandwidth, our transmission rate will be much faster. Data rate and bandwidth are proportional to each other. If we need a higher bandwidth, if we need a higher speed, we need a higher bandwidth. For example, like your home internet system, Unify, for example, right? If you see that, if you go for the higher speed, for example, from 100 mega to 500 mega or 800 mega, the price would be different. Why is it like that? Okay, why does the internet provider plays with the speed of transmission? Okay, because the speed is depending on the bandwidth. How much bandwidth that needs to be given to you in order to achieve a higher data rate. So if you need a higher speed, that means the internet provider needs to give you wider bandwidth. So bandwidth is money. Okay, bandwidth is money. If you need more bandwidth, you need to pay more. Okay, and then what? Additional circuit. Analog signal must be converted to digital pulse and converted back to analog. So the circuit is more complex. Okay, and then it needs a precise time synchronization between transmitter and the receiver. Transmitter and receiver must be synchronized in terms of time. Okay, so the transmitter cannot suddenly send the signal. So both of them must synchronize in terms of time. So that means the receiver must be aware when the transmitter wants to send the signal. Okay, and then it is incompatible with a certain older transmission technology. Okay. Okay, so this is the transmitter and receiver system. Yeah. So this is the transmitter and receiver system for digital. So this picture is taken from the Bernard Scala's book, Digital Communication System book, which is used by the student who will take the subject of digital comm. Okay, so so the above picture here is a transmitter. Okay, the above part here is a transmitter, and the below part here is a receiver. Okay, so you see that there are many processes happens inside the transmitter and receiver. Okay, so formatting. Okay, I will briefly explain about the process. So the first process is format or formatting process to convert analog to the digital. Okay, and then source and code is compress the data so that we can save a lot of bandwidth. Encryption is for data security. Channel encode means that we encode the data, okay, by inserting additional bits in order to make sure that the system is able to detect and correct error at the receiver later. So we do the encoding. So encoding means that we might add additional bits for the purpose of error correction and also error detection and also error correction. Okay, and then we can multiplex the data with data from other sources. Okay, and we can do the modulations later using a pulse code. Okay, so PCM pulse code modulation, we can convert it as a digital pulses, okay, from digital data to digital pulses. Or if you want to transmit as a analog, that means we need to do the bandpass modulate. We need to modulate our input signal with the analog carrier. And frequency spread here is also a part of modulation process if we have many inputs. Multiple access is a process of multiplexing of wireless signals from different sources. Okay, and then we transmit the signal to the medium. Okay, and then we do the reverse process. Okay, we do the reverse process until we get the original output. Okay, so what you will learn in chapter 4 is not all the process. Okay, you will learn about formatting, you will learn about PCM. So PCM will be in your task 2. So for second task of your project, I suggest you to download the MATLAB from the website using your student's account, because UTHM subscribe to MathWorks. You can download and use freely the MATLAB software, okay, for the task number 2. Okay, so this is the simplified block diagram. Okay, we have the information source, the input, source encoder. As I mentioned previously, source encoder is actually to compress the data so that we can reduce the bandwidth usage. Channel encoder, we encode the data by adding additional bits to the data so that we can do the error detection and error correction later. Digital modulator, if you want to transmit as wireless, that means we need to convert the digital data into electromagnetic wave, which is analog. That means we need to do the modulation with analog carrier to produce either ASK, amplitude shift keying, or frequency shift keying, or phase shift keying. Then we transmit through the channel, okay, and then goes through the receiver, okay, digital demodulator, channel decoder, channel source decoder, and also information. We produce the original information source. Okay, so this is the description. Information source can be analog or digital. Okay, source encoder is to here to make the data smaller, as I mentioned earlier. Channel encoder is for the error and error detection and also error corrections. We do the encoding process, we add additional bits to the data. Okay, and then digital modulator, we modulate the input with the analog carrier to produce the electromagnetic waves. Okay, so that means here it will produce amplitude shift keying, ASK, or frequency shift keying, or phase shift keying. Okay, channel is a medium. It can be guided or unguided transmission medium. Okay, guided means using a cable such as fiber optics. Unguided means a wireless medium or free space. And these are the several processes in the each of the block diagram. Okay, so in formatting, you will learn about sampling, quantizations, and also the encoding process. Okay, source coding, there are predictive coding, block coding, variable length coding. So we will not learn about this. So this chapter will focus on formatting, and then baseband signaling. Baseband signaling is the process of modulation, okay, or encoding process without using analog carrier. Okay, so baseband signaling means that we are sending the signal in the form of baseband frequency, low frequency. That means we are not going to modulate the input with the analog carrier. Okay, instead we are using a baseband encoding in this process with the line coding. Okay, so you will learn about this. Equalizations, so this is not in the syllabus. And then a bandpass signaling. Bandpass signaling, we will learn about this. Bandpass signaling, there are coherent and also non-coherent. So what is coherent, what is non-coherent, you will learn about later. Okay, so here we will, this is for the bandpass transmission, where we transmit along the wireless medium. Okay, so you will learn about ASK, FSK, and PSK. Okay, ASK, FSK, PSK. And then channel coding, there are many types of channel coding. Okay, memory signal, antipodal, orthogonal, trellis coded, structured sequence, block codes, convolutional, turbo codes. So these are not in your syllabus. Okay, you will learn this in the digital communication subject. Okay, but for chapter 4 we are not going to learn about this. Okay, synchronization also not include in this syllabus. Okay, multiplexing also not include in the syllabus. So you see that there are many things not included in the syllabus. Okay, spreading also not included in the syllabus. Okay, encryption also not included in the syllabus. So you see that we have eliminated a lot of processes in the digital com, so that easy for you to study. Okay, but for students that will take the digital communication subject, the communication elective subject, they will learn a lot of these things in the subject. Okay. Okay, the first process, which is the formatting process. Okay, so formatting process consists of 3 processes. The first one is sampling, then we do the quantization, and then encoding. So these are in sequence. First we do sampling, then we do quantization, then finally do the encoding. So the purpose of formatting process is to convert analog to digital signal. Okay, that means we want to convert analog from continuous time signal into a discrete time signal. Okay, the first one, sampling. Okay, so for your information, we always ask this process in the final exam. Explain about the sampling, quantization, and coding process. So this has been asked frequently in the previous semesters. Okay, pernah ditanya banyak kali. At least you understand the concept. Okay, at least you understand the concept. What happened in the sampling? What happened in the quantization? What happened in the encoding? Okay, so let's look for the first process, which is sampling. So sampling is a process of changing continuous time signal into discrete time signal. Okay, so amplitude values at specific time interval are taken at using a sample and hold operation. Okay, the method is sample and hold operation. The output of this sampling process is what we call as the pulse amplitude modulation signal. Okay, and you see that palm signal is as in this picture, palm signal. Okay, that means we are taking, you see that we have the input, our input is analog. Okay, and actually we want to take sample, sample. Okay, we take sample. So we take sample at certain time. Okay, at a what we call as a sampling time. Okay, so you see that the signal now becomes discrete time. What is discrete? Discrete means it is not continuous. Okay, so in this example, the sample is taken at Ts. Ts is sample time. Okay, and if you see from here, actually, if we take many samples, we will produce a more accurate output. Why is it like that? You see, if I take many samples, I will produce a palm signal which is very similar to the continuous time signal. Kalau saya ambil sampel lagi banyak, saya akan produce palm signal yang lebih accurate, yang hampir sama dengan analog. Okay, so the concept here is that the higher the number of samples that we take, the more accurate will be the output. But there's a drawback. If we take a lot of samples, we need wider bandwidth. So that there must be a give and take between the number of samples and also the bandwidth requirements. Okay, so how much is the sampling rate? Okay, sampling rate is Fs. Okay, Fs, so Fs is equal to 1 over sampling time. Okay, and Fs defines the number of sampling per second. How many sample should I take in 1 second? That's the sampling rate, Fs. Okay, Fs adalah kadar sampling. Okay, so according to the Nyquist, okay, Nyquist is a mathematician, with derived the mathematical equations about this probability of signals. So in his mathematical derivations, he come to the conclusion that the sampling rate must be more or equal to the 2 times the highest modulating signal frequency. Siapa tu? Boleh mute microphone? Tolong mute microphone. Siapa tu? Pelajar tolong mute microphone. Can you please mute your microphone? I can hear noise over here. Siapa tu? Oh, Usama. Is it? Could you please mute your microphone? Okay. Okay, according to Nyquist, he said that the minimum sampling rate must be equal or more than 2 times of the highest modulating signal frequency. So if we have more than one input modulating signal, we should take the highest modulating signal frequency. Okay, and from here we can describe the sampling time. Okay, the sample time would be equal or less than 1 over 2 FM. So this is actually mathematical. If you convert from here, because TS is equal to 1 over Fs. Okay, TS is equal to 1 over Fs. So if you want to find the TS, that means TS is equal or less than 1 over 2 FM second. Okay, so this is the sampling time. Okay, FM is a message signal frequency or modulating signal frequency. Okay, so therefore the minimum, okay, from here, the minimum Nyquist rate, the minimum sampling rate, what we call as the minimum Nyquist rate, is equal to 2 FM. So this is the minimum. So sampling cannot be less than this. Okay, it can be more, but it cannot be less than this. Okay, so the higher the sampling rate would be better actually. Okay, I repeat again, the higher the sampling rate would be better, because we can produce more accurate output. However, as I mentioned earlier, it will consume a lot of bandwidth. So there must be a give and take between the sampling rate and also the bandwidth requirements. So if the sampling rate less than 2 FM, what happens is that there are going to be overlapping of adjacent signal channel, okay, in the frequency domain, which is what we call as the aliasing. So aliasing is the overlapping of symbols in frequency domain, okay, which looks like this. Okay, so if we sample more than 2 FM, if we sample more than 2 FM, the channel symbol is separated at a suitable distance. There's no overlapping. But if we sample less than 2 FM, there's going to be overlapping of the adjacent channel symbols, okay, which is this one. So this is what we call as the aliasing, overlapping. Okay, if overlapping happens, the receiver would be unable to distinguish between one channel and another channel. Okay, receiver akan menghadapi masalah untuk membezakan antara dua channel bersebelahan. Okay, so this is what we call as the aliasing, and this is if we sample less than 2 FM. Okay, so this is picture is in frequency domain. Okay, you see that this picture is in frequency domain. How to convert in frequency domain? Of course, it is through the Fourier transform and so on. So you learn about that in signal and system subject, but you will not learn here in this chapter. So we are not going to learn again about the Fourier transform process. Okay. So sampling. So how to do the sampling? Now, how to do the sampling? So there are three methods. The first method is impulse sampling, and then natural sampling, and then flat top sampling. Okay, so impulse sampling. So you see that when we do sampling, we are actually do the process of multiplication in time domain. We multiply two input signal in time domain to produce the sample output. Okay, so if you see from here, the input signal analog is multiplied in time domain with the delta function or the impulse function, okay, to produce a palm signal. Okay, so palm signal is still analog, it's not yet digital. Okay, remember, palm signal is still analog, it's not yet digital. Okay, so what happened when we do the multiplications? You see that when we multiplied analog input with the impulse train function, okay, in time domain, we're going to produce y delta t like this. Okay, so you don't need to memorize the equation. Okay, you don't need to memorize the equations. The equation is shown here just to show you what happened when we do the multiplication in time domain. Okay, and then natural sampling. So natural sampling, the difference with the impulse sampling is the pulse train that we multiplied with the analog input. So now the pulse train that we use is the rectangular pulse train. Okay, in the natural sampling, we multiplied the analog input with the rectangular pulse train. Okay, so the difference is in terms of this, PT is different. And when we multiplied with the xt, the input, it becomes like this, yt at the output. So the output here, the pump signal shows that the amplitude of the output follows the shape of the input signal. Okay, so you see that the shape of the pump signal follows the shape of the analog input. So this is why we call it as natural, because the output is naturally follows the shape of the input. Again, you don't need to memorize the equation. You just need to understand that sampling is the process of multiplication of two signals in time domain. Okay, and then what? Flat top sampling. So this is the flat top sampling is the most popular sampling process. Okay, in the real world. Okay, in the real world, in the practical system, we normally use a flat top sampling. Okay, of course, there's a lot of there's a many types of flat top sampling depending on the application type. Okay, so flat top sampling means that the top of the sample signal is flat. Okay, so how to do that? Okay, how to do that? And you see that so the flat top sampling involves multiplication in time domain and also involve convolution in time domain. Okay, so it is produced through the convolution. Okay, it produced through the convolution. Wait, Okay, so it produced through the convolution in time domain of PT. PT is the rectangular pulse signal with y delta t. So y delta t is from the impulse sampling. So in the impulse sampling, if I flash back, y delta t is here. So if we do the multiplication of the analog with the impulse function, we produce a y delta t. And from here, we do the convolution with the rectangular pulse train PT. Okay, we do the convolution with the PT, and we're gonna get the flat top pump signal. Okay, so you see that we do the convolution in time domain with y delta t. Okay, this is y delta t, and we're going to produce a flat top sample at the output. So you see that the top of the sample is flat. So that's why it is called as a flat top sampling. So there's a reason why we use a flat top sampling. One of it is to reduce the noise. The noise is reflecting about the errors actually. So that's why we use a flat top. We commonly use a flat top sampling. Okay. Okay, so let's do the example. Okay, example 6.1. example 6.1, audio signals are often sampled at different rates. Okay, CD audio quality is sampled at 44.1 kilohertz rates, while quality audio sample is telephone quality audio is sampled at 8 kilohertz. What are the maximum frequencies in the input signal that can be fully recovered for these two sampling rates? Briefly describe the theory you used to obtain the results. Remember, sampling rate, the minimum sampling rate is 2 times FM, 2 times the modulating signal frequency. That means FM here is the highest input. If we have many input frequencies, we need to choose the highest input frequency. Okay, the highest input frequency. Okay, so the question asks you, what is the maximum input frequency? That means we need to divide the sampling rate given in the question with 2. Okay, for example, CD audio's quality, CD quality audio, the maximum frequency given in the question is 44.1 kilohertz. That means the highest input frequency is 44.1 divided with 2, so we get 22.05 kilohertz. While for the telephone quality audio, given in the question, the maximum sample frequency, the sample frequency is 8 kilohertz. So therefore, the highest input frequency is sample frequency divided with 2. So we get 4 kilohertz. So this is what we call as the highest FM. Okay, this is the highest FM. And the question asks, briefly describe the theory you used to obtain the results. So we obtained the result based on the Nyquist theorem. Nyquist said that the sampling frequency must be at least twice the highest frequency of the component in the input signal. Okay, so Nyquist said that Fs must be equal or more, okay, than 2FM. Okay, FM here is the highest input frequency. Okay. 6.2. If an arbitrary means a randomly chosen input signal is directly sampled, what is the undesired effect that may cause and how to solve this? So if we randomly choose the input signal and then we straight away do the sampling process, there's gonna be a problem of aliasing. Maybe. Okay, there might be a situation if we randomly choose an input without considering how much is the input frequency. If we don't consider that, there might be a problem. They might be causing the aliasing effect. Okay, so aliasing effect, there might be this is happen if we sample with a rate less than 2FM. Okay, that means the input frequency is higher than the sampling rate. Okay, so to solve this problem, that means we need to make sure that the input frequency is lower. To ensure this from not happening, we need to introduce a low pass filter. Okay, so that low pass filter before the sampling. So low pass filter will select low frequency signal. Okay, we'll select a low frequency signal to make sure that the higher frequency signal is not passed through the system. So if we only select a low frequency signal, we can eliminate the potential of aliasing effect in the system. Okay, kita boleh mengatasi masalah ini dengan menggunakan low pass filter kerana low pass filter ini akan pastikan hanya low frequency sahaja dibenarkan masuk ke dalam sistem and the higher frequency will be removed. Okay. Example 6.3. Nah, what is the Nyquist sampling rate for each of the following signals? How much is this? Okay, a low pass remember sampling rate, minimum sampling rate is equal to 2 times the highest input frequency. Okay, so the question asks what is the sampling rate, okay, for the following signals. A low pass signal with a bandwidth of 300k. Okay, a low pass signal means that like this, starting from 0. So this is a low pass signal from 0 until f. Okay, with a bandwidth of 300. So that means over here the distance 300 kilohertz. Okay, so that means f here is 300. Okay, so you see that the first solution, in a low pass signal the minimum frequency is 0. Okay, and from 0 we already been given in the question that the bandwidth is 300 kilohertz. So therefore, okay, therefore the maximum frequency is of course 300 kilohertz. Okay, so from the picture that I've drawn here, we see that the highest input would be at 300k. Okay, if the minimum is 0, that means with a bandwidth of 300 kilo, that means the highest frequency would be 300. Okay, 0 plus 300k. So that means the highest frequency, the highest FM would be 300 kilohertz. So therefore, the minimum Nyquist rate Fs is equal to 2 times the highest input frequency. So therefore we get 2 times 300,000 or 300k, so we get 600,000 or 600 kilohertz. Okay, so the unit here is sample per second, or you can also use hertz. Okay, you can use sample per second or you can use hertz. Similar, same. Okay, tidak ada masalah. Okay, and then what? A band pass signal with a bandwidth of 200 if the lowest frequency is 150 kilo. Okay, so if you draw the band pass signal, it looks something like this. Okay, band pass signal. So this is a F. So it said that the bandwidth is 200 and the lowest frequency is 150. So how much is this, the highest frequency? So the highest frequency, okay, let's say this is FM. So FM, the highest frequency is 150 kilohertz plus the bandwidth 200 kilohertz. So we can determine the highest modulating frequency, which is 350 kilohertz. Okay, so from here we can calculate the sampling rate. So sampling rate is equal to 2 times the highest input frequency. So we get 700,000 sample per second, or 700,000 hertz. It's the same. Okay, do you have question to ask? You can ask question. Otherwise I will move to the next topic. Okay, kalau ada soalan boleh tanya. If you have question, please ask. Otherwise I will move to the next topic. Okay, so this example is straightforward regarding the sampling rate. Okay, sampling rate, normally we ask in the exam, calculate the sampling rate, quantization and so on. So this is the beginning, which is the sampling rate. Sampling rate minimum is 2 times the highest input frequency. Okay, so you can sample more than 2 FM. It cannot be less than that. If you sample less than 2 FM, there's going to be aliasing effect. Okay. The next is quantization. So after sampling, we need to do the quantization. Okay. Before I proceed, can I get your response? Are you still there? Anybody can respond?
Yes, betul.
Okay, thank you for the response. So sometimes I am afraid that I'm talking to myself. Okay. The next is quantization. Remember, we need to do sampling process first. Okay, after sampling, sampling process, remember about Fs larger or equal than 2 FM. So we produce a PAM signal, pulse amplitude modulation signal. So PAM signal is still an analog signal. It's not yet digital. Okay, belum jadi digital lagi. Okay, so quantization. Okay, so quantization is the process of assigning the sample values into a finite set of values. So remember, when we take the sample, we take sample. So there are many values of samples. Okay, so we need to assign the sample values to the nearest quantized level. Okay, so how to do this? Maybe I should maybe I can draw. Wait, I want to insert new slide. I need a new slide so that I can draw. So I will draw here. Okay, so here is a quantization. So quantization is the process of assigning the sample values in the sampling process into a finite set of values. Okay, so the sample value can be taken from the specified value of the quantized level. So actually, in the quantization, we are actually rounded up the sample value to the nearest quantized level. So apa yang berlaku di sini, kita akan membundarkan nilai sampel yang kita ambil tadi kepada nilai quantized level yang terdekat. Okay, so what happened actually? Something like this. So let me do the drawing. So remember that initially we have the analog signal like this. Okay, so this is the analog input. So this is a voltage versus time. For example, this is VMT, for example. Okay, then we do the sampling. Okay, we do the sampling. What happened is, so what happened is that for example, sorry, my drawing is not good, so maybe I delete this, for example, wait, so I'm trying to illustrate the process so that easy for you to understand. Okay, so for example, like this is the input VMT. Okay, and when I do the sampling, I will take sample. Okay, so for example, I take sample, I take another sample, I take sample, so I sample at TS, 2TS, 3TS, and so on. Okay, so here something like this. Okay, so this is 4TS, 5TS, for example 6TS. Okay, so again this is voltage versus it's too long. Okay, so this is NTS. Okay, so this is a palm signal. Okay, so I take sample. Okay, so you see that the values of the sample. Okay, so there are many values of the sample. Okay, so this I have 6 values of sample. Okay, I have 6 maybe 6 different values of sample. So this is if I take 6 sample. If I take thousands of sample, there's gonna be big problem. Okay, because the range of values are very big. So what I need to do is that I need to round it up the values to the nearest level, to the nearest voltage level. Okay, so I need to do the quantization. Okay, so when I do quantization, so let's say I have 4 different level. For example, so this is for example Q0, Q1. Okay, so I will round it up the sample value to the nearest quantized level. If you see from my example, okay, so the first sample will be rounded up to Q2. Q means quantized level. Again, this is still in term of voltage. Okay, dia masih dalam analog. We still in analog. Okay, and second sample is I rounded up to Q3, for example. Okay, and then sample 3 I rounded up to Q2, quantized level number 2. And here for the fourth sample, I rounded up to the Q1. And then sample number 5, I rounded up to Q0. And then sample number 6, I rounded up to Q1. Okay, so you can say that, for example, Q0 is for example minus 4 volt, for example, minus 2 volt, 2 volt and 4 volt here, for example. Okay, so Q quantized level is in the form of voltage level. Okay, so you see that the sample can be any values from the original signal. We take sample, many sample. In the real world, it's actually thousands or millions of sample we take per second. Okay, remember in the practical system, we may take thousands or millions sample in 1 second. So imagine that we have a lot of values, sample values. So this will make difficult for the next process, signal processing. What we need to do is we need to round it up the sample value to the nearest quantized level, we are actually do the rounded up process. Okay, rounded up adalah pembundaran. We rounded up, for example, lower value to a little bit higher value, or higher value to a little bit lower value, anywhere near the quantized level. Okay, so again, this is still TS, 2TS, 3TS. Okay, the sampling time, 4TS, 5TS, 6TS, and so on. Okay, so what you can see from here, I'm actually rounded up the sample value to the nearest quantized level. So imagine I have 6 different values of sample. I rounded up to 4 nearest quantized level in my example. Okay, which is more easier for me to do the signal process if I only refer to 4 levels only, for example. Okay, rather than 6 or more different values. Okay, and remember, when we do the rounded up process, we rounded up the sample value to the nearest quantized level. So that rounded up is actually, we are introducing error. Okay, for example, my sample is let's say 1.8 volt. I rounded up to 2 volt, the nearest quantized level. For example, contoh okay, or for example, my sample is for example 2.1 volt. I rounded up to 2 volt. So when we do the rounded up process, we are actually introducing error. Okay, the error is the difference of real value, the original value, with the rounded up value. That's the error. Okay, we are actually making the error actually, but it is a very small. Okay, it is very small, and we can compensate the error later. This is not a big problem. Okay, remember, rounded up is actually making the error actually, but it's very small. Okay, and it will not disturb the quality of the signal. Okay, and if you see from here, how many levels that I need, how many quantized levels that I need, there's another question. So the number of quantized level is equal to 2 power of n. N is the number of bit used in the system. Okay, in my example, I have 4 levels. That means I use 2 power of 2 in my example. Okay, dalam example saya gunakan 4 levels. That means I'm using 2 bit. Okay, so what is 2 bit? Okay, so 2 bit means that the system will process every 2 bits input. Okay, so if I have 4 levels, that means I have 4 different codes, which is for example, here you see that I have Q0, Q1, Q2, Q3, Q4, sorry, Q3. So that means this is, since I'm using 2 bit, that means this is 00, this is 01, this is 10, and this is 11. So this is the codes for each of the quantized level. So we will learn about this later. So now you see that the quantized level, the number of levels is actually 2 power of n. And remember, the higher the levels would be better. Lagi banyak jumlah level, lagi bagus. Okay, so normally the number of bit is wider. For example, you can use 10 bit, 20 bit. So higher number of bit can be used in the system. Okay, and if we have a higher number of levels, if we have many quantized levels, that means the process of rounded up would be less. Okay, we will rounded up the value to a smaller range of values, which is the error would be less, very small. Okay, so imagine if I have many levels, that means I just need to round it up just a few decimal point only to the nearest quantized level. So the range of error would be smaller, which is good. Okay, so it is good to have many quantized level, but again, if we use higher number of bit, we need higher bandwidth. There's a pro and cons. Okay, we can use a higher bit, okay, higher number of bit, we can have many quantized level, but we're gonna consume a lot of bandwidth. So there must be a give and take about bandwidth and also the number of bits used in the system. Okay, so again, so we back here. So I already explained about this picture. So this picture is actually similar to my picture, except that this is only a positive side of cycle. Okay, so the number of levels is 2 power of n. N is the number of bit. Okay, and when we assign the quantized level, normally we use a Q0 from the lowest amplitude to the highest amplitude of Q. Okay, this is how we do the labeling of the quantized level. Okay, and you might wonder this one, the step size. How big is the step size? If we look from my example, how big is the distance? Okay, how much is the distance from one level to another level? How much is the distance? So the distance, okay, in my example, I'm using a same distance for each level. Okay, in my example, that means the distance here, or what we call as a step size, the distance, step size between each level is guided by the formula of what we call as the step size or resolution. Okay, so in this example, the resolution or the step size is equal to the Vmin. Okay, the minimum voltage. Okay, so we're going to learn about this later. Okay, what is the Vmin or the step size? Okay, resolution or the step size is the distance between each quantized level. Okay, so you're going to see later that quantization consists of uniform quantization and also non-uniform quantization. So in this example, I'm using the same step size. Okay, there's also possibility that we are using a non-uniform step size where the distance between each level is different. It can be also like that. Okay, so here the step size, okay, the size between the distance between each level is what we call as the resolution. Okay, and then what? Quantization error. So this is what I mentioned earlier. When we rounded up the value, we are actually making the error. Okay, so the error is what we call as the quantization error. Okay, it is defined as modulus sample value minus quantized value. Okay, so the maximum quantization error would be step size divide with 2. Okay, step size divide with 2. So this is the maximum. Okay, resolution divide with 2, or step size divide with 2. So QE, also known as the additive white noise, which happens in all frequencies, or what we call as a white noise, happens in all frequencies. So it is also known as the QN, quantization noise. So error is also the noise. In digital, the error is considered as the noise. Okay. So you see that, for example, if the sample value is 1.6, I rounded up to the nearest quantized level 1.5. That means the error would be 0.1 volt. Okay, and this is the quantized error, or the quantization noise. Okay, and the maximum QE would be so we need to know the resolution divide with 2. So we're going to see the example later about this. Okay, this one. So you see from here, okay, from here, this is the signal. Okay, first we do the sampling. We take the sample 1.3 volt, 3.6, 2.3, 0.7, minus 0.7, and so on. When we do the sampling, then we do the quantization. That means we round it up to the nearest quantized level. So what is the quantized level in this example? So the quantized level starts from negative 3.5 until 3.5. Okay, so we have 8 different levels. Okay, we have 8 different levels, and this is using 3-bit. Okay, 3-bit means 2 power of 3, we got to get 8. So we have 8 levels. Okay, so the range is between minus 3.5 until 3.5. Okay, and the distance here, if you see the distance, the step size or the resolution, how much is this? This is, if you see from here, the distance is if you see from here, the distance is 1 volt. So that means the step size is 1 volt, or the resolution is 1 volt in this example. Okay, and if you see from here, we have 8 quantized levels. Okay, from minus 3.5, minus 2.5, minus 1.5, minus 0.5, 0.5, 1.5, 2.5, and 3.5. Okay, so for example, if the sample value is 1.3 volt, we need to round it up to the nearest quantized level, which is 1.5 volt. Okay, so you don't need to see the last 2 lines. The last 2 lines is about encoding process, which is the next process. Okay, so we want to see this process at quantized level. Okay, the second sample is 3.6. Okay, which is this one. So the nearest quantized level would be 3.5. Okay, and then third sample is 2.3 volt. The nearest quantized level would be 2.5. Next, if I take 0.7 here, you see 0.7, sample 0.7, the nearest would be 0.5 quantized level. So you see that we rounded up the sample value to the nearest quantized level. Okay. Example. So this example is important. So your final exam will be something of in this range of topics. Okay. So let's do the example here based on figure 6. Figure 6 is this one. Figure 6. Determine the resolution. So from this example, we can straight away determine the resolution, the step size, which is the distance between 2 quantized level. You see that the difference is 1 volt. We can say straight away from this example. you can measure the step size. The difference between two levels is 1 volt in this example. So that's why resolution, the step size or the distance between two levels is 1 volt. Okay, and then what? The maximum quantization error, QE max. So QE max, according to this example, according to this equation, it is actually resolution divided with 2 or step size divided with 2. Okay, so step size divided with 2 or resolution divided with 2. So the maximum error that possible happen in the system is equal to resolution divided with 2. So 1 volt divided with 2, so we get 0.5 volt. Okay, half of the resolution. This is the maximum error that possible to happen inside the system during the quantization process. Okay, and then what? Find the quantization error for sample number 1, 2 and 3. So sample number 1 is 1.3 volt, 1.3 volt, 3.6 volt and 2.3 volt. Sample number 3. Okay, so 1.3, second sample 3.6 volt, third sample is 2.3 volt. So when we do the quantization, we rounded up 1.3 to the nearest level is 1.5. Okay, the nearest would be 1.5. Okay, from 1.3 becomes 1.5. 3.6 we reduce to 3.5. 2.3 we increase to 2.5. So the rounded up process can be up and down the values. Okay, so here is the quantization process, quantization value. 3.6 become 3.5, 2.3 we rounded up to 2.5. Okay, so the error, if you see from here, the error would be the difference, sample value, so modulus, okay, modulus sample value minus quantization value. Okay, so 1.3 minus 1.5 modulus, so we get 0.2 quantization error. 3.6 minus 3.5 modulus, we get 0.1. 2.3 minus 2.5 modulus, so we get 0.2 volt. Okay, so these are the errors, the rounded up value. Okay, the rounded up value. Okay, do you have question to ask? You can ask about this. Okay, so this is based on figure number 6. Okay, based on figure number 6. So if you don't have question, let's do the next example, 6.4b. Okay, so 6.4b, so this is also about the quantization process. You see that the voltage range of analog to digital converter that use 14 bits, that means n equal to 14. So the quantization range, okay, is between -6 to 6 volt. Find the number of discrete levels, binary codes that are represented, then the number of voltage increment used to divide the total range, voltage range, and the resolution of the digitization expressed as the smallest voltage increment. So this is taken from the Frenzel's book. Okay, this is taken from the Frenzel's book. Okay, so the number of levels, the number of levels is depending on L equal to 2 power of n, which is 2 times 2 power of 14, because we are using 14 bit. So the number of levels, the number of quantization levels is 16,384. Okay. And then the question asks, how much is the number of voltage increment used to divide the total voltage range? So the second question asks, how many step size? Okay, the second question is actually asking you how many step size. So if we have 16,384, how much is the ladder, the step size? Okay, for example, like in this example, maybe I can relate this one. How many step size? How many levels? How many, not the level, how many step size in the quantization? So the step size is actually excluding the zero voltage, which is less than one value less than the total levels. It is one value less than the total level. Okay, it defined as how many steps. Okay, how many steps? Level is level. Okay, how many resolution actually? Okay, so in this case, it is actually one value less than the total level. Okay, so you will learn actually this in the next topic actually, which is what we call as the dynamic range, DR. Dynamic range is the number of step size that we use to divide with the total range of voltage. So the range of voltage is between -6 until 6. Okay, so like this. So from 6 volt, and also here, for example, minus 6, for example, over here. Okay, so this is 0 volt. Okay, so the level is actually excluding the 0. When we want to assign the step size, we are excluding the 0 volt. Okay, so now the issue, question number B, is actually asking how many level that we need, okay, to assign the voltage, between the range from -6 to 6. How many steps that we need, which is excluding the 0 volt, excluding the x-axis. So it is equal to the total level minus the 0 volt. So the total number of what we call the number of voltage increment that we need is actually 16,383, one value less than the total number of levels. Okay, and this is also known as the dynamic range. Okay, you will learn later about the dynamic range. And then question C asks you the resolution. So now we want to determine how much is the resolution, how much is the step size. Okay, step size is the range from one level to another level. Okay, the distance. Resolution is the distance from one level to another level, or what we call as a step size. Okay, so resolution is equal to the range of voltage, 6 volt minus 6, divide with the dynamic range, 2 power of n minus 1. Okay, so that's why you get 12 volt divide with 16,383. So this is the levels excluding the 0 volt. So we get 0.7325 millivolt. Okay, so that means the distance or the step size between one level to another level is 0.7325 millivolt. Very small. Okay, very small. If you see from the previous example, in this example, the resolution is 1 volt in this example. Okay, every step size, the difference is 1 volt. But in that example, the step size or the distance between one level to another level is 0.7325. Okay, and if you see from here, from minus 6, let's say the last would be minus 6. So if you want to know what is the second level, okay, over here, for example, how much is that actually? So actually it is minus 6 plus 0.7325 milli. So the next level would be will be minus 5.9992675. So the next level will be at 5.992675 volt, and so on. You need to plus with 0.7325 millivolt. For example here, okay, how much is the next level? So 6 minus 0.7325 milli. So over here is 5.9992675, and so on. Okay, so there are 16,000 levels. Okay, so in the previous exam we have asked this kind of question, but not up to 1,000 level. Okay, so up to 8 level is normal. Okay, up to 8 level is normal. So we have asked the student to determine how much is the level, how much is the voltage for each quantized level. We have asked this kind of question. Okay, so when you know the resolution, when you know the range of voltage, you can determine the step size. You can determine how much is the voltage for each level. Okay, remember this has been asked a few times. Pernah ditanya, where the student have been asked to determine the voltage for each level. When you want to determine the voltage of each level, make sure you know the range, make sure you know the resolution, and make sure you know how many levels. So the step size would be the total range of voltage divided with dynamic range, 2 power of n minus 1. So you get the resolution or the step size. From there you can go one by one. Either you want to go from the minimum or you want to go from the maximum to the minimum. Either way is okay. Okay, so here if I want to find the next level, for example here, the next level would be, I need to minus this value with resolution with 0.7325 milli, and so on. Okay, so you can try on your own. Try practice. You can use this example. For example, you want to find 8 values below 6 volt and 8 values above -6. You can try on your own. But this one is 16,000, so you don't need to do all. So normally we ask student in the exam up to 8 level or 16 level. Okay, pernah ditanya. We have asked this kind of question. Okay, determine the voltage value for each quantized level. In order to do that, make sure you know the range, make sure you know how many levels. Okay, from there you can find the step size. Okay, so it's already 5 o'clock, so I have to stop. Okay, so we stop here. Okay, we stop here SQR. So you can take your QR code reader. Okay, take your QR code reader and you can scan the attendance. Okay, so see you again next week. Okay, and make sure you can complete the the project task 1. Make sure you can complete the project task 1 by the given date, I think 28. So you can take the attendance and then you can go to anywhere you like. Okay, so see you again next week.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Doctor, can you take my name?
What's your name?
Sundus.
Sundus? Wait.
Okay, doctor.
Wait for the rest who want to scan the QR code.
Okay, thank you, Doctor.
Okay, welcome.
Saya Dr. Nuramira.
Why you cannot scan? Why many of you cannot scan the QR code? What happened?
Internet lambat lah doktor, dia macam tak detect.
Okay. Yeah. So the first one before this is what? Sundus. Okay. And then what?
Nurul Amira.
Nurul Amira.
Nurul Amira.
Nurul Amira. Okay, done.
Saya Dr. Muhammad Khairul Hafiz.
Thank you, doctor.
Muhammad apa?
Khairul Hafiz.
Muhammad Khairul Hafiz. Khairul Hafiz Abdul Rahman. Okay, done.
Thank you, Doktor.
Okay. Who else?
Saya Doktor, Syahim Azim.
Siapa?
Syahim Azim, number 22.
Syahmi Azim Sungip. Okay.
Nombor 8, Doktor.
Number 8. Siapa? Kumaran.
Kumaran Naidu.
Okay, done. Any more?
Thank you, Doctor.
Okay.
Muhammad Amri, Doctor.
Muhammad Amirul Amri.
Muhammad Amri Adam, yeah.
Okay, done.
Thank you, Doctor.
Okay, welcome. Who else? Okay,
Doktor,
Apa, Hamshari?
kan
Wait. Hamshari tak boleh nak scan ke? Okay, Hamshari, wait Hamshari, Muhammad Hamshari. Okay, Hamshari, done. Okay.
kan kesana tu doktor.
Okay, welcome Sundus. Okay, Hamshari dah settle.